Algebra by Michael Artin. Chapter 2, Groups. Section 2, Subgroups. One reason that the general linear group and the symmetric group are so important is that many other groups are contained in them as subgroups. A subset H of a group G is called a subgroup if it has the following properties. 2.1. A. Closure. If A is a member of H and B is a member of H, then AB is a member of H. B. Identity. 1 is a member of H. C. Inverses. If A is a member of H, then A inverse is a member of H. These conditions are explained as follows. The first condition, A, tells us that the law of composition on the group G can be used to define a law on H, called the induced law of composition. The second and third conditions, B and C, say that H is a group with respect to this induced law. Notice that 2.1 mentions all parts of the definition of a group except the associative law. We do not need to mention associativity. It carries over automatically from G to H. Every group has two obvious subgroups, the whole group and the subgroup 1, consisting of the identity element alone. A subgroup is said to be a proper subgroup if it is not one of these two. Here are two examples of subgroups. 2.2 Examples. A. The set T of invertible upper triangular 2x2 matrices. Matrix A, B, blank, D, A and D not equal to 0, is a subgroup of the general linear group GL2R. B. The set of complex numbers of absolute value 1. The set of points on the unit circle in the complex plane is a subgroup of CX. As a further example, we will determine the subgroups of the additive group Z plus of integers. Let us denote the subset of Z consisting of all multiples of a given integer B by BZ. 2.3. BZ equal the set n a member of Z such that n is equal to BK for some k a member of Z. 2.4 Proposition. For any integer B, the subset BZ is a subgroup of Z+. Moreover, every subgroup H of Z+ is of the type H equal BZ for some integer B. Proof. We leave the verification that BZ is a subgroup as an exercise, and proceed to show that every subgroup has this form. Let H be a subgroup of Z+. Remember that the law of composition on Z+ is addition. The identity element is 0, and the inverse of A is negative A. So the axioms for a subgroup read: 1. If A is a member of H and B is a member of H, then A plus B is a member of H. 2. 0 is a member of H. 3. If A is a member of H, then negative A is a member of H. By axiom 2, 0 is a member of H. If 0 is the only element of H, then H is equal to 0Z, so that case is settled. If not, there is a positive integer in H. For let A member of H, be any non-zero element. If A is negative, then negative A is positive. And axiom 3 tells us that negative A is in H. We choose for B the smallest positive integer in H. We claim that H is equal to BZ. We first show that BZ is a subset of H. In other words, that BK is a member of H for every integer k. If k is a positive integer, then BK is equal to B plus plus B k terms. This element is in H by axiom 1 and induction. So is B of negative k equal to negative BK by axiom 3. Finally, axiom 2 tells us that B0 equals 0 is a member of H. Next, we show that H is a subset of BZ. That is, that every element n, a member of H, is an integer multiple of B. We use division with remainder to write n equal BQ plus R, where Q and R are integers, and where the remainder R is in the range R greater than equal to 0, less than B. Then n and BQ are both in H, and axioms 3 and 1 show that R equal n minus BQ is in H2. Now, by our choice, b is the smallest positive integer in H. while r is greater than equal to 0 less than b. Therefore, r equals 0 and n equal bq is a member of bz as required. The elements of the subgroup bz can be described as the integers which are divisible by b. This description leads to a striking application of proposition 2.3 to subgroups, which are generated by two integers a and b. Let us assume that a and b are not both 0. The set 2.5 az plus bz equal the set n a member of z such that n equal ar plus bs for some integers r and s is a subgroup of Z+. It is called the subgroup generated by a and b because it is the smallest subgroup which contains both of these elements. Proposition 2.3 tells us that this subgroup has the form dz for some integer d, so it is the set of integers which are divisible by d. The generator d is called the greatest common divisor of a and b for reasons which are explained in the following proposition. 2.6 proposition. Let a and b be integers, not both 0, and let d be the positive integer which generates the subgroup az plus bz. Then a. d can be written in the form d equal ar plus bs for some integers r and s. b. d divides a and b. c. If an integer e divides a and b, it also divides d. Proof. The first assertion, a, just restates the fact that d is contained in az plus bz. Next, notice that a and b are in the subgroup dz equal az plus bz. Therefore, d divides a and b. Finally, if e is an integer which divides a and b, then a and b are in ez. This being so, any integer n equal ar plus bs is also in ez. By assumption, d has this form, so e divides d. If two integers a and b are given, one way to find their greatest common divisor is to factor each of them into prime integers, and then collect the common ones. Thus, the greatest common divisor of 36 equal 2 times 2 times 3 times 3, and 60 equal 2 times 2 times 3 times 5 is 12 equal 2 times 2 times 3. Properties 2.6, 2, and 3 are easy to verify, but without proposition 2.4, the fact that the integer determined by this method has the form ar plus bs would not be clear at all. In our example, 12 equal 36 times 2 minus 60 times 1. We will discuss the application of this fact to arithmetic in Chapter 11. We now come to an important abstract example of a subgroup, the cyclic subgroup generated by an arbitrary element x of a group G. We use multiplicative notation. The cyclic subgroup H generated by x is the set of all powers of x. 2.7. H equal the set ... x to the negative 2 power, x to the negative 1 power, 1, x squared, ... This is the subgroup of G, the smallest subgroup which contains x. But to interpret 2.7 correctly, we must remember that x to the n is a notation for a certain element of G. It may happen that there are repetitions in the list. For example, if x is equal to 1, then all elements in the list are equal to 1. We may distinguish two possibilities. Either the powers of x are all distinct elements, or they are not. In the first case, the group H is called infinite cyclic. Suppose we have the second case, so that two powers are equal, say x to the n power equal x to the m power, where n is greater than m. Then x to the n minus m power is equal to 1, by the cancellation law 1.12. So there is a non-zero power of x, which is equal to 1. 2.8. Lemma. The set S of integers n such that x to the n equal 1 is a subgroup of Z+. Proof. If x to the m power is equal to 1 and x to the n power is equal to 1, then x to the m plus n equal x to the m times x to the n is equal to 1, 2. This shows that m plus n is a member of S if m and m are members of S. So axiom 1 for a subgroup is verified. Also axiom 2 holds because x to the 0 power is equal to 1. Finally, if x to the n power is equal to 1, then x to the negative n power is equal to x to the n power times x to the negative n power is equal to x to the 0 power is equal to 1. Thus, negative n is a member of S if n is a member of S. It follows from lemma 2.8 and from proposition 2.4 that S equal mz, where m is the smallest positive integer, such that x to the m is equal to 1. The m elements 1, x, x to the m minus 1 are all different. If x to the I equal x to the j with I greater than equal to 0 less than j less than m, then x to the j minus I is equal to 1. But j minus 1 is less than m, so this is impossible. Moreover, any power x to the n is equal to one of them. By division with remainder, we may write n equal mq plus r with remainder r less than m. Then x to the n power is equal to x to the m power to the q power times x to the r power equal x to the r power. Thus h consists of the following m elements. 2.9. H is equal to the set 1 x x to the m minus 1. These powers are distinct and x to the m is equal to 1. Such a group is called a cyclic group of order m. The order of any group is the number of its elements. We will often denote the order by 2.10. The order of G equal the number of elements of G. Of course, the order may be infinite. An element of a group is said to have order m, possibly infinity, if the cyclic subgroup it generates has order m. This means that m is the smallest positive integer with the property that x to the m power equals 1, or if the order is infinite, that x to the m power is not equal to 1 for all m not equal to 0. Example, the matrix 1, 1, negative 1, 0 is an element of order 6 in GL2 of R, so the cyclic subgroup it generates has order 6. On the other hand, the matrix 1, 1, 0, 1 has infinite order because the matrix 1, 1, 0, 1 to the nth power is equal to the matrix 1 n 0, 1. We may also speak of the subgroup of a group G generated by a subset U. This is the smallest subgroup of G containing U. It consists of all elements of G which can be expressed as a product of a string of elements of U and their inverses. In particular, a subset U of G is said to generate G if every element of G is such a product. For example, we saw in 1.17 that the set U equal x, y generates the symmetric group S3. Proposition 2.18 of Chapter 1 shows that the elementary matrices generate GLN. The Klein 4-group V is the smallest group which is not cyclic. It will appear in many forms. For instance, it can be realized as the group consisting of the 4 matrices 2.11, the matrix plus or minus 1, 0, 0, plus or minus 1. Any two elements different from the identity generate V. The quaternion group H is another example of a small subgroup of GL2 of C, which is not cyclic. It consists of the 8 matrices 2.12. H equal the set plus or minus 1, plus or minus I, plus or minus J, plus or minus K, where 1 equal the matrix 1, 0, 0, 1. I equal I, 0, 0, negative I. J equal 0, 1, negative 1, 0. K equal 0, I, 0. The two elements I and J generate H, and computation leads to the formulas 2.13. I to the 4th power equals 1. I squared equal J squared. Ji equal I to the 3rd power J. These products determine the multiplication table of H. Algebra by Michael Artin, MIT. This book was published in 1991 by Prentice Hall. It is read by Jim Renholt with programming and illustration by Jim Renholt, 2019. Thank you for listening.